And we're live, I think. Of course, we require some kind of external confirmation of our existence. Hey, everyone. Welcome to another completely random interview chosen by my guest, the time and place. Today's guest, Dr. Brendan Dyck, a fellow West Coaster. Brendan, how's it going?
It's going well. Thanks for having me on.
So the question I always ask, who are you? What do you do?
So I am a geologist. I'm what they call a metamorphic petrologist. So I mostly study the evolution of mountain belts on Earth, and formation and migration and generation of earthquakes at depth. But a lot of the tools that I use kind of revolve around thermodynamics. And it turns out everything we've learned about thermodynamics and applying thermodynamics to understanding Earth evolution is very relevant when we're looking at other planets. And so I'm a geologist who's taking a step over to astronomy, and so far had a very welcome reception, but we'll see how that goes.
Well, it's funny. I mean, you mentioned that you're a petrologist, so that's an oil geologist, right?
Oh, that's a petroleum geologist.
Oh, okay.
Petrology is just the study of minerals and their formation.
Oh, okay. I see. So when I saw your name, yeah, so that was exactly it. And then, of course, you were saying that you came from Elder, but you went to the University of British Columbia, as did I. So we share an alma mater, although I ditched out after my first year of engineering and went into computer science instead. And you, I guess, kept with it, and now you're a professor?
Well, yeah, I've bounced around a bit. I did my master's over in Sweden. I did a PhD in the UK, postdoc in the UK. And then I was at Simon Fraser University in the Lower Mainland, and now I'm at University of British Columbia.
Yeah, that's amazing. Are you in the Lower Mainland, or you're in Kelowna?
I'm in the Lower Mainland right now.
Yeah. Okay. All right. Well, then you are literally just a ferry ride away from where I am.
Georgia Strait.
Yeah, exactly. Yeah, we share a body of water. So then, what caught my attention was you, I guess, or your public relations official had posted a press release yesterday, a couple of days ago, just about how, your thinking in geology has helped narrow the focus, give us some new thinking about what it means for a planet to be habitable. So can you sort of give us what was sort of considered the traditional idea of what was meant to have a habitable planet?
For sure. So I'm sure a lot of your listeners are familiar with a habitable zone. So an orbit close enough, but not too close to a star where you could support liquid water on the surface of the planet. And there's a lot of parameters that affect this. It's not just how much heat you're getting from the star, it's how thick your atmosphere is, how much of a conductive blanket you have. But it's a broad zone. And if you can find a rocky planet that lies within that zone, that's as close as you're going to get to a first filter on finding an Earth-like planet. And that for a lot, up until quite recently, that's been the goal for, I shouldn't say goal, but that has been a desire for some astronomers to be able to find planets, and especially observe smaller Earth-like planets, which is more difficult within a habitable zone. But just because a planet lies within the habitable zone, it doesn't mean it's going to have surface water. And Mars is a great example of that. It's just on the outskirts of the habitable zone in our own solar system, and it is barren, right? It's dry. And done some previous work on this, but we relate to it in this more recent study. The reason for that, or one of the main reasons for that, is because early on in that planet's history, the development of the iron core of that planet, that sets the eventual surface composition and the surface thickness, the thickness of that crust that forms on that planet. And depending on the crust you form on a planet, over the long period of times or long time scale that a planet evolves, we're talking billions of years, it either will or it won't support water. So it's either going to be a thickness of a crust or a composition of a crust that potentially could soak water in and hydrate. That may have happened with Mars, or it could be too thin of a crust, in which case you might initially have water on the surface, but you have no mechanism of recycling that water down into the mantle and deeper down in the crust and then returning back up through volcanism. And so on Earth, it's really that cycling and a development of tectonics that we think, as geologists and other scientists that study this, think this is probably very important for the development of life.
We've got another example. You mentioned Mars, and Mars is like 1/10 the mass of the Earth and cooled down pretty rapidly early on in the solar system formation. And so it seems very like it would have to have very special circumstances for it to really be a good place to live so many billions of years later. But we've got another example of a planet in the habitable zone around our sun, and that's, of course, Venus, with exactly the same or roughly the same mass as Earth, and yet catastrophically different, both in terms of its atmosphere, but also in terms of its actual, the rocks, and it doesn't have, has a very different composition. So does that play the role, do you think?
Yeah, so despite it being so close, or one of our neighbors, we don't know so much about the composition of Venus, but we can make some pretty informed inferences based off what we know of the other inner planets. And it likely does have a very similar composition to Earth. And it likely even has a similar distribution of iron between its core and its mantle, which is what we talk about in this most recent study. So yeah, it's a great candidate. But where Venus likely has gone wrong is in its potential to develop and maintain some form of mobile lid tectonics, where you have equilibrium between the atmosphere and the lithosphere, and a balance, right, where you can sequester and maintain some of that CO2, not just in the atmosphere, you can bring it back down into the lithosphere. And so that's an example of a runaway greenhouse effect, which is something we desperately want to avoid at all costs here on Earth.
Well, we talk about the tectonic plates here on Earth, right? And you've got these two plates, the continental plates, and you've got the oceanic plates, and the continental plates are thicker, right? And they float on top of the mantle in a way that the oceanic plates don't. Do we, when we look at the history of Venus, we see this sort of all these resurfacing events where the entire surface of Venus literally just turned itself inside out. Is that a plate problem?
It's a great question. There's been a lot of geologists, tectonicists that have studied the surface and what we know of the surface of Venus, and there's what have been called tesserae. So striations, long lineaments that are observable on the surface that don't look too dissimilar to what a mountain belt appears from space on Earth. That being said, it's missing some of the key criteria that we'd use to recognize tectonics here on Earth. So it is an open question. Perhaps it had tectonics. There's certainly a camp of geologists who would believe that it did support maybe mobile or plate tectonic style, or a plate style of tectonics, but it certainly doesn't now. So that's also an interesting question. Why did it stop? Because it seems very stable on Earth. Tectonics has been active on Earth roughly 3 billion years now, and as far as we understand, it hasn't stopped in that time.
And I mean, part of the problem is that Venus sucks. And so it's just really rough to try to image it up close. We've got these incredible high-resolution images of Mars down to like a 1 meter accuracy, and we don't have anything of the sort on, from Venus. Like the best is Magellan, and I think it's like 30 meters per pixel or worse. Could better resolution scans of Venus give you that answer, do you think?
Probably not just with surface morphology. Now, that being said, we've learned a lot about Mars with just surface morphology. I think having composition of the crust of Venus, having a better understanding of the interior structure of Venus, like we're trying to do with Mars with the InSight mission, that's really where we're going to get those answers.
Right. Okay, so we've got a sense right now. It's just this blunt instrument. Could water form on the planet? And that's where the conversation ends. And so what you propose is a fine-tuning of the features of the planet and how they will interact with the water. So let's talk about that some more.
Sure. Yeah. So one major variable that kind of falls out of the observations that astronomers are able to make of exoplanets, not even just within our own solar system, is the core mass fraction. And so this is a this is a way of thinking about how large is the core relative to the rest of the planet. And so it breaks the planet down to a mantle, which is everything that's not the iron core, and then you've got the iron core. And what's the mass difference between those? And this is where it gets really interesting from a geology perspective, because astronomers can look at the composition of stars, and there's an implied assumption here that the composition of a planet mirrors that of the star. It's an assumption that has proven correct for almost all cases that we've looked at, certainly in our own solar system. And it intuitively makes sense if they're all accreting out of the same nebula to begin with, or the accretionary disk to begin with. But that is an assumption that goes in here. They have this composition of a star, and from that, they say that's the same composition of a planet. And based off of that, they say, well, all the iron will go into the core, and all the magnesium and silica. And if you have magnesium, silica, iron, add oxygen in there, that accounts for about 90 to 95% of the weight of all the elements that make up these inner planets. So they're pretty content with stopping there, and they say all the silica and magnesium, that's going to go into the mantle.
Right.
And that's fine. That's a great, first pass assumption. But then we look at our own solar system, and the Mercury, probably Venus, but certainly Mercury, Earth, Mars, and then some of the other bodies like Vesta, they've all got the same bulk composition. If you put them in a blender and rehomogenize them, you'd find them to all be, at least in the refractory elements, they'd all have the same composition. And that is the composition that matches that of our sun. Now, I'm going on a track here, but what I'm trying to get at is what's really interesting is, despite us all having the same composition in our inner planets here, if we look at the amount of iron in our mantles, it's wildly different, right? And that's because not all iron goes into the iron core, right? The more efficient core formation is, the larger that iron core will be, and more of the iron will be in the core, which is going to leave a very iron poor mantle. And that'll be something like Mercury, right? Large iron core, iron poor mantle. Earth is somewhere in the middle. We've got about 8% of our mantle is made up of iron. Whereas if you go to Mars, 20 to 24% of its mantle is made up of iron. So much, much more iron, which means that it was a less efficient core formation. And so that distribution of iron was more oxidized, and it made it out into the mantle.
So is that just a factor of the mass of the planet that's pulling that? Like with Mercury and Mars, they're smaller and less massive than the Earth, and so the iron forms into the middle. Is that?
They're on the opposite spectrum, so
right.
They're both smaller than in mass, so less massive than Earth, but Mercury has very little iron in its mantle, whereas Mars has a lot.
Okay.
It likely reflects the position in that accretionary disk. So as you go further away from the star, there's an oxidation gradient, and so you become more oxidized. And it's a very simple chemical reaction here, where iron plus oxygen becomes iron oxygen, or iron oxide, FeO, and the iron oxide is the species of iron that exists within the mantle, whereas the metallic iron is what exists within the core. And so if you create that core, and you're efficient in creating the core, all that iron is going to go down into the center. So the point here is that despite all these inner planets having the same composition, their core mass fractions are wildly different. And so astronomers are in this position of assuming that all iron goes into the core. And now this is not all astronomers. Some astronomers in planetary sciences are developing ways to more creatively look at the distribution of iron, not just in the core, but in the mantle. And what we show in this study is, if you follow that track and you can work out the composition, the amount of iron in the mantle, that is actually a very key parameter for predicting the thickness and the evolution of the crust. And that's going to impact the surface evolution of a planet, ultimately its habitability.
And so if we were able to do a better analysis of Venus, we would probably find a iron density in the core that was in line with...
commensurate to Earth.
Right.
It would be similar to Earth, yeah.
But closer to the sun.
Kind of independent.
Right, but also closer to the sun, and so maybe a little more iron in the core then. And so And so when you extrapolate that idea, you're looking at, I guess, the metallicity of the star overall to see how much just raw material you've got to work with in the solar system. And then you've got this distribution of that iron starting close into the star and leading out. And then you guys have to overlay that with the habitable zone to give you some sort of idea.
Yeah, that's exactly it. So if we think about it in terms of there being an oxidation gradient away from each star, then perhaps if planets stay where they formed, they didn't migrate too much, then perhaps we can use that as a filter, or with maybe with direct imaging, we'll start to get some surface compositions, or based off atmosphere compositions, might be able to infer surface compositions, and we can start working out what the mineralogy and iron content would be at the crust. So yeah, I think we're going in the direction of getting these answers.
And so then, what specifically is this iron mix? How is that causing or encouraging habitability or discouraging habitability?
Yeah, sure. So iron oxide, out of the oxides that make up the mantle, there's about 10 of them, major oxides. Iron's got the lowest melting point. So if you put more of it within the mantle, it reduces the melting temperature of that mantle. And so what that means is over the lifetime of a planet, as it's warm and it starts to cool, if it's got a lower melting point in its mantle, that mantle will continue to melt, which translates to crustal formation and volcanism. So that will occur over a longer period of time if you have a lower melting point, right? Because these planets are cooling through time. And if you cool to the point where you're now colder than the melting point, you're not going to have any volcanism derived from that mantle, right? That's very basic, but that really kind of is what it boils down to. So increasing the iron content of your mantle will result in more voluminous crust production, a thicker crust, and then it also impacts the composition of that crust that forms. And it happens to be that the crust that forms in a more iron-rich planet, so something like Mars, can hydrate more efficiently, right? And so that the actual minerals that form in that crust can take hydroxyl and water into its structure, so much so that Mars might have drunk up to twice a global ocean in its mineral structure within its crust and mantle.
Yeah, I've heard that, and this is a fairly recent discovery that it really looks like the oceans. People always thought that the oceans on Mars were lost to the solar wind, and because of Mars' low gravity and the hydrogen atoms escaping out into space, and now it really looks like Mars just soaked it all up and became dry, and yet all that water is still locked away in rocks. Pretty fascinating idea. And so what are the implications then for habitability for just a typical planet as you're sort of starting to move across the Milky Way and look at various extrasolar planets?
I guess it's another filter you have to apply where you're looking at Earth-like planets, rocky planets within the habitable zone, and then you're also now looking at the composition of their mantles and the resulting composition of their crust within that habitable zone as a filter or a way of evaluating over the long term. And that's really a point we have to stress here is initially all these planets could have had water, right? But it's how they're able to retain it over the long time scales that's necessary for example, evolution of complex life. We need billions of years for this to occur.
Yeah. And I guess, and here's the tricky part, which is how could one try to get some sense of what's out there and to see if the rest of the Milky Way matches our understanding of what's happening here in the solar system?
Yeah. And so that's where if we can get better measurements of core mass fraction of extrasolar planets, we're going to, we can, once we have that information, and again, we make that implied assumption that the bulk composition is the same as the star. It's a pretty common assumption that's being made, but it is an assumption. So if we make that assumption, bulk composition, and we know the core mass fraction, that narrows down the composition of that mantle enough that geologists like myself can make some informed predictions of what that surface will look like.
Right. Because my understanding, is that astronomers have tried to make some kind of connection between the metallicity, even the kinds of elements that they're seeing in the star, to try to predict which ones are going to have exoplanets, more exoplanets, and so far that's been tough to find. They haven't been able to make that connection.
Yeah, it is, and when you get down to this really falls into the realm of petrology and geology, because you're talking about how do different compositions impact the mineralogy or the stratification of the lithosphere. And this is where there's 50 plus years of experimental and natural observation research in petrology that can be tapped into through thermodynamics to answer these questions. And so, we've got models, ways of using thermodynamics to simulate the formation of these minerals in all range of conditions that have been developed on Earth that are actually quite applicable to not all exoplanets, because there's some very, very different compositions and very different pressures and temperature gradients, but certainly applicable to the majority of them.
Yeah, it's pretty interesting. So, we're all probably very familiar with the Drake equation as this idea of like searching for intelligent civilizations across the Milky Way. And when it comes to habitability, it's very simplistic, I think. You've got how many stars, how many have planets, what planets are in the habitable zone, and then it quickly shifts to other factors of how many to go on to develop life, etc. But if you stick on that planet itself, what do you think, if you were to sit down and write the new Drake equation where you just took that one variable of the habitability of a planet and expanded it out and out and out and out, how many factors do you think would be in there in a vastly revised Drake equation?
Well, I'm only going to comment on once we get to the term in that equation when we get to planets, because it's stuff that comes
you don't have to worry about how many civilizations don't destroy themselves or so on and so forth.
Right. But once we get into those planetary terms, I think an important point here is that a lot of these important variables are actually correlated. So to have the right iron content in the mantle also likely implies you have the right size of core, an iron-rich core, that you might be able to support a magnetic field like we have on Earth. And that's a really important one for the evolution and the protection of surface life, right? And so that's why I say some of these may be correlated. So we might be able to put, every geologist you talk to, you could probably put another variable in that would be valid. But I think we'd find that if you start plotting these up, a lot of them would correlate, and we could probably lump them together. And I would say that the distribution, the formation of the core, the size of the core, and the distribution of iron from the mantle, or between the mantle and the core, should be one variable, and that's probably one variable that is not currently in the Drake equation, but could explain quite a few of these planetary processes.
Right, but when I sort of think of all the things that I've seen, like the presence of a large moon, the presence of a magnetosphere, the thickness of an atmosphere, the water on the surface, et cetera, et cetera, et cetera, you're saying that a lot of those will express nicely from the ratio of the iron in the core to the mantle.
Yeah, that it's a bold claim, but yeah, I think that's the case, and the reason why is because a lot of this has to do. So in one hand, it would be developing the magnetosphere, right? So having the right size iron core is going to help you with that, and right temperature of iron core. But then in terms of the thickness of the mantle, or the composition of the mantle and the lithosphere that forms above that, that's going to impact whether or not you're going to have plate-style tectonics that could evolve. And once we develop plate tectonics, now we have this recycling and buffering mechanism for the atmosphere. And so we're tuning to get as close as we can to an Earth-like planet. And maybe an Earth-like planet with plate tectonics isn't the only planet that could have life, but it's the one we know works.
Yeah. Yeah, well, I mean, we're even just in terms of astrobiology, there's more and more evidence that the most habitable places in the solar system are not the places like Earth. I mean, Earth is the best, but beyond that, it's not about Mars. It's possible it's places like Europa and Enceladus, where you've got the right conditions for life underneath the ocean. They are tricky to observe. Are there any sort of versions of that even on terrestrial planets where conditions could be alternative and yet still support life theoretically?
Yeah, one idea that I really am kind of drawn to is this idea of a stagnant limp planet. So a planet that doesn't have plate tectonics, but it's tidally locked with its star. And so same surface is aiming it all the time. Now you've got hemispherical differences in what that atmosphere temperature and composition might be. And you might get recycling between hemispheres rather than in between the atmosphere down into the lithosphere and back, right? So it's a different way of thinking about that recycling. And those might be, you might see a ring of potential habitability in a planet like that, where it's not too hot, not too cold. You're verging on sci-fi here, but I think that is, if you ask, a very different environment that potentially satisfies what we're looking for. That might be one of them.
Yeah, that's really interesting. That you would have sort of a region of habitability that's more under the surface, but quite vast. So, I mean, I asked this question earlier just about like what's it going to take to be able to confirm the hypothesis, and mostly your opinion is check more stars, try to get a connection between the stars and their planets. But if if money was no object and you were able to devise some kind of experiment to be able to, I guess, to figure out if this factor is happening, what would it take to be able to really know the iron mix of planets across, even within a few light years of us?
Yeah, that is another great question. I think I think the whole money is no object has already probably been spent with James Webb, and I'm really optimistic that information we'll get from James Webb will give us a lot of important information, both in terms of the composition, the presence of an atmosphere and the composition of an atmosphere. But a lot of astrobiologists really are looking for those life signatures in the atmosphere, which is great, and I'm all for that. But they're probably going to ignore planets that have no atmosphere. And from a geology perspective, those are fantastic, because now we're imaging the surface,
yes.
Right? We're imaging the rocks. And that's going to tell us so much information. And I'm optimistic that quite a few planets that we'll be looking at, or that will be looked at with James Webb, will be close enough to their stars. They probably have no atmosphere, and we'll get some direct imaging, maybe of compositions, bulk surface composition. That will tell us a lot, because we'll know the bulk planet. And if we know the bulk surface, we kind of have the beginning and the end of the process. And geologists, that's enough that we should be able to work out what's happened in between. But we might also be able to identify the difference between continental and oceanic crust, in which case we have a case for tectonics to be made.
Right. There's also been this idea of like magma planets out there. Yeah. And that would be, I guess, a situation where the rock is the atmosphere, because it's being sprayed out by the volcanoes, which would give you another line of evidence. One of the most powerful ways to, or I guess one of the first ways to find things in physics, astronomy, particle physics, things like that, is indirect evidence that you can use to kind of tie together this story. And sort of one example that I've been thinking about is NASA is currently thinking of putting an observatory on the far side of the moon to detect the longest wavelengths of radiation. And one of the things it's going to be able to do is it's going to be able to detect the interactions between planet magnetospheres and their stars. So you literally discover exoplanets because of the radio emissions coming from their magnetospheres. Does a magnetosphere tell you anything about a planet?
From our understanding, it tells you you've got a shielded surface, right?
Yes.
And it's shielded both in terms of, you're shielded from potential photolysis and stripping of an atmosphere by solar radiation, but it's also shielded in the sense that you don't have high energy particles bombarding your surface. And for life, maybe some high energy particles are important, but probably not too many of them. So I would think that there are paleomagnetic folks that will tell you that's the most important thing you have to have at magnetosphere. And they're probably right. It's probably very important.
Right. But I'm just sort of wondering if you could get those observations, if someone could hand you, here are all the stars, here are the strengths of their magnetospheres and the distances from their stars across these 1,000 planetary systems, would you be able to infer the dynamo that's causing those magnetospheres and thus try to get a sense of the iron in the planets.
That's a very creative, and I like the way you're thinking. I hadn't thought about that. And
well, there you go.
I think you probably would be able to do that. You could probably say something about the size and the temperature distribution through that liquid core, and from that you could say something about perhaps how large that core is, how much iron is in that core relative to what would be in the mantle. So it'd be an alternative way of trying to get at this parameter that I'm claiming is an important parameter.
Yeah, so. Yeah. And sort of another example is just this idea of observing the atmosphere, that like if you couldn't see the surface of the Earth, but you could just smell the atmosphere, could that tell you anything about the geology of the planet?
Yeah, absolutely. This is a new field of research, but a very active field of research. And it should not actually be a surprise, but it turns out the atmosphere is in equilibrium with the lithosphere to some extent. So what you have at the surface, the mineralogy, the weathering that occurs at the surface, and what is actually there to be weathered, that directly influences and impacts what you have in your atmosphere. So these are two different layers that can be in equilibrium. And if your surface is recycled through, say, tectonics, that will impact your atmosphere as it would changing the composition of that material. So that is, as I understand, that's a field that probably needs more work, more fine-tuning before we could say this is a composition of the crust, but it's definitely going in that direction.
Apologies, people listening. Someone's working on the outside of my house, and so you're going to hear some hammering. Hopefully, it won't happen too much. So, I mean, that's again, I sort of like this idea. We're sort of changing the regime from finding individual planets to finding thousands of planets. Eventually, it'll be with Nancy Grace Roman telescope, it's going to be hundreds of thousands of planets. With future surveys, it's eventually going to be millions of planets. And so it stops being, I joked about this, we no longer, we won't even bother reporting. You tell us we found a planet, we're not interested. Wake me up when you found 7 in a system or something. So does that, are you shifting your work towards these sort of larger scale data mining of larger databases, or in general?
Yeah, absolutely. In general, there's some great catalogs being assembled of the compositions, the mass radii of these different planets, as well as the stars of the orbit. And these are very, very useful resources for geologists like myself who can look at these composition or density parameters and think about it in terms of what's giving us that density, that apparent density. It's one thing to just say it's rock, it's a rock envelope, but it turns out there's a whole range of rocks, right? And what might be there is actually quite important in terms of thinking of what how that planet has evolved or how it might evolve. So yeah, absolutely. And I was going to say, alongside with this mass of data that's coming in, we're also getting new forms of data as well, right? So there's refinements being made in how precisely the mass or the radii of a planet is being measured, as well as the composition, going from direct composition of the star and inferring over to perhaps direct imaging of composition of the atmosphere or the surface. So yeah, these are new forms of data that will certainly add to this vastly growing body of observations.
As a geologist, where would you like to, if you could be on a trip to Mars or a trip to some other place in the solar system and use your toolkit to chip away at a rock or two, where would you love to go? And again, sort of money, no object, you can survive any condition. So go to Venus, dig down into Jupiter. Where would you like to go in the solar system?
That's a great question. Mercury. I would love to know more about the surface of Mercury. It's amazing the information we have from missions to Mercury. It's got a very interesting history. It has way too much iron, so it's either been added iron in or it's lost everything else. That's also probably potentially the case. Understanding what's happening on a planet like that, from the results of this recent study we put out, it would suggest that even if Mercury didn't have this history of either adding iron in or losing its mantle or mantle crust, it still would have been inhabitable because it was such an iron poor mantle, and it would have formed very, very thin crustal veneer. But I'd love to see what that looks like and confirm, what volcanism and style of volcanism on a planet like that would look like.
Is there a landscape on Earth that would be comparable, that you could walk around on that landscape and go, this is kind of Mercury? Because there's lots of places that are kind of Mars, but is there a kind of Mercury?
Yeah, I was thinking both in terms of the structure and the composition here. In terms of the composition, you're looking for something that's would be very iron poor.
Like a slag heap? I'm just sort of, I guess the opposite, iron poor, so not a slag heap.
Opposite,
yeah.
Yeah, I mean, some continental crust, but in that case, it's very silicic. I think in terms of the thickness, you could look at some very anomalously thin portions of oceanic lithosphere, where you have a higher heat flow from the mantle, and that would be more Mercurian.
So where would that be? Where does this exist on Earth?
You can step on the rift in Iceland, right? You can look at where the North Atlantic is dividing, and you've got in some areas thinner portions, less developed portions of oceanic lithosphere. We could do that with any mid-oceanic ridge on Earth, but not all of them are exposed at the surface. Many of them are beneath the oceans. But
right. But not like a lava flow in Hawaii or something. I'm sort of imagining like that's a place I've walked around, and you've got the sharp, jagged lava, and you've got the the smoother, the pahoehoe. Yeah. It's sort of like rippling liquid, but and I have been to Iceland, but I didn't sort of remember specifically what it felt like to be walking on the rift.
Well, here's what for you. One thing that would be unique about Mercury would be the low iron content of its magma. And what we know from experiments here on Earth is adding iron to your magma reduces your viscosity. Right. And so if we look at things like a Yellowstone, where you've got volcanoes that are hundreds, if not thousands of kilometers in diameter and only a couple kilometers height, like huge shield-style volcanoes, those are more iron-rich. They have lower viscosity, and they run for a long time, that magma. If you're very iron poor, you're going to get clumpy, explosive magma. You're not going to get these large shields. So the surface, perhaps, of course, the gravity impacts us as well, but ignoring that for a time being, your surface would be more jagged, and it would be sharper conical features.
Right. Okay. So I'd love to take some questions from the audience as well. So if you've got some questions for Dr. Dyck, please let me know, and I will pass them along. And of course, Arjun has jumped in here with a bunch of questions. So I'm going to find my favorite one. So he asks, could you say that a planet has continents if you find mountain ranges or at least tectonics? So if we had a telescope powerful enough to see mountain ranges on another world, would that tell you something?
Yeah. So if you could see Arcuate mountain ranges, and you could see evidence of two plates colliding together and having a deformation zone, that would be about as good. Well, I shouldn't say about as good, but it would be a great line of evidence that had mobile laid style of tectonics. And I say that as a difference to say plate tectonics, where plate tectonics is really what we have operating today. Large plates that are in continuous movement, but mobile laid, at least you have rigid plates or lithospheric plates that are moving relative to one another.
Right.
Yes. Mountain range would be a good one.
Six Bob Ohms is asking a question that's not exactly about what we're talking about, but I'm going to sort of adapt it, which is off topic. It wants a new episode on planetary defense. Have you thought at all about the geology of asteroids and as that relates to trying to stop them from smashing into Earth?
I haven't.
Okay, all right.
Good question, but the composition, most of that material that you find in the asteroid belt is more oxidized. So it goes in the direction of Mercury. And Vesta would be the most oxidized of the larger bodies that have been studied. So you're looking at a thing that's even more on the Martian side of thick crust, iron-rich crust.
Right. It's interesting. The evidence seems to be that there's actually, like, you can literally trace now all the asteroids back to just a few planetesimals that were around early on in the solar system, and very few of those still remain. The rest are just the smashed up and reformed versions of these rubble piles at this point.
Yeah.
And so you probably could reconstruct what these planetesimals were like if you could sample more and more of these asteroids and start finding these common features, which would be kind of interesting, because that would fill in the missing gaps between, because all you've got Mercury, Venus, Mars, and Earth, but in fact there were probably another 100 early on in the solar system that would fill in all those gaps.
Sure, and there is some perhaps very stochastic element here when you get into planetesimals colliding together. Is a planetesimal differentiated before it collides in with our planet? And for the formation of the moon, that's something that would have had to have happened. So yeah, that becomes a very interesting line of research. And how chemically evolved are these planetesimals before they collide?
A couple of people are mentioning Titan in the comments, and one of the cool things about Titan and the rest of the outer solar system is that it is like geology, except you're just shifting the matter. So instead of having volcanoes of molten rock, you've got volcanoes of ice, cryovolcanism. Instead of rock made of rock, you've got rock made of ice, and instead of glaciers made of ice, you've got glaciers made of ammonia or nitrogen. Would you, if you were dropped off in the outer solar system, would your skills as a geologist still work, do you think?
Yeah, I think we could look
shift?
for broad scale similarities. We could look for the style of recycling on a planet, right? Is it just through a vent or like a volcano, or is it through plate motion? To some extent, I think so. And at the end of the day, where the skills would overlap is thermodynamics of water, thermodynamics of ammonia, and the phase diagrams that you construct with all the different phases of ice are very similar to what we would construct with rock. So there is a lot of overlap, but I would have to shift my chemical thinking.
Yeah, but I just sort of imagining that you would be able to sort of walk along a ravine and see weathering or whatever of ice and go, okay, well, that, if I was on Earth, that would be rock, that would be, that would be a glacier. Glacier would have caused these, if you see big remnant chunks of ice sitting in the middle of a ice sheet, you'd be like, well, maybe that's a glacial remnant that's left behind. It's sort of interesting to think about how it all just comes down to temperature, how all of these things shift.
And ice is a mineral, right? And so technically a glacier is a rock.
Yeah. I mean, ice is a crystal, rocks are crystals. It's sort of a similar function, just based on temperature.
For sure. Actually, the crystalline nature of ice leads itself very well to thinking about deformation and the rheology, the flow of this material in the same way we do with the mantle and we do with the crust here.
The moon, a couple of people are talking about the moon as well. And the moon is, an interesting idea as a time capsule of the solar system and even the universe, that there's like these layers of regolith that trap a history of what happened in the solar system, and even, again, all of the cosmic rays that are bombarding the nearby supernovae. What would you like to find out if you could get your hands on core samples from the moon?
Yeah, I'd love to see a better understand what the current thermal and mechanical structure of the moon as you go deeper down. It's got an enormously thick lithosphere. It's smaller, it's cooler, and it's all solidified, but there may still be some motion or some warmer mantle that might be moving down deep down close to what core or some small core of the moon. So just knowing more about that structure would be really fascinating.
Arjun is asking as well, have you figured out what stars would be the best chance of making the planets that fit your research? Do you have a favorite star at this point that you're going to want to go and look at?
No, but I'm actively in the process of looking through these catalogs and saying, okay, let's so in one hand with this study, we looked at it from not looking at any particular star, but looking at the process, forming a core. How does that impact the evolution and the development of the surface on a planet. But now we're saying, well, let's use these tools and let's see all the information that's been captured from, a certain exoplanet and the star that it orbits. Let's use that information to make predictions about that exoplanet. And so, if any of your listeners has a favorite that you think there's great precision on mass and radii and composition, let me know.
Well, then allow me to propose one, which is the K star.
Okay.
Yeah, the K stars are less massive than the G stars like the Sun, but they're more massive than the M dwarfs, the red dwarfs, and so they are much longer lived than G stars, and so you've got a long time for really interesting factors to play out, and yet you don't have sort of these rapid changes that are happening with the star. But with the M dwarfs, they're so awful at the beginning. They cast out these really deadly flares that probably strip away the atmosphere from the planet. There's even arguments about whether or not they're even habitable. But there's been, if you do some search into like super habitability, the K stars come up over and over again as places that are literally more habitable than the Earth. Not for us, but for other, for that you can have a higher density of biology, of diversity on a planet orbiting around a K star than you could around either an M dwarf or a G star. So I think, if you don't have a favorite, allow me to propose one.
Well, then now I need a particular K that's got observed exoplanets, and then we can go down.
There are some, yeah, and they're easier to find exoplanets because they're less bright, they're less massive, and so you've got a better shot of finding an exoplanet around it as opposed to something more like the Sun. So yeah, my hope is for the K stars. Adam Synergy asks, is the habitability of water worlds tied to geology? And this is sort of a really interesting idea, this proposal that there are these water worlds where the water could be tens of kilometers, hundreds of kilometers thick, and then interacting with the lithosphere under enormous pressure and possibly even temperature. Have you had a thought about what that might look like?
Yeah, for sure. And I think the key is when you need a certain thickness and pressure and mass of these volatile or water envelopes, gas envelopes, to perhaps make this boundary layer where you are not actually getting that much interaction across the lithosphere into the wet outer layer. And so in that sense, it might be a case of where the accretion has gone in a direction where there might have been equilibrium between that lithosphere, chemical equilibrium between the lithosphere and the water layer that got outpaced, and then it becomes this stagnant boundary layer where there's very little interaction. So in that sense, geology kind of plays second fiddle, and it's not really impacting very much what's happening in that outer layer. But you could imagine how certain forms of geological activity might disrupt that boundary layer and start to get recycling or re-equilibration. So maybe it's the long-term longevity of a layer like that geology might have more of a role in predicting.
I mean, I wonder if there's a thickness of the ocean where there is no way to get the minerals from deep down into a place where they're closer to the sunlight and usable by life.
Certainly, yeah. There's people work within that term, that the thickness of these layers and the mass of these layers, and they can be enormous values, but yet perhaps it doesn't need to have to be even that enormous for it to be.
So Loose in Space is having a conversation with the rest of the chat, just generally about this question about whether or not we're certain that chemistry as we understand it here on Earth is going to work the same in other places around the solar system and even in the universe. And so, sort of starts to feed into the anthropic principle and the Copernican principle. Do you feel pretty confident that the rules of chemistry as we understand them will play out in the same way across the universe?
Yeah, I think the laws of thermodynamics are pretty immutable in this case, and where chemistry might be different is in the starting composition. And if you're wildly different in your starting composition, then our mineral structures will be different. We won't have silicates, for example, as the main Earth and all the inner planets, mantles and crusts are silicates, different versions of silicates. But you can get into very rare environments, even on Earth, where they are borosilicates. There's so much boron that they become borosilicates, or you can get into oxides where there's no silica involved at all. Iron oxide, copper oxide, or sulfides. You can imagine all these different mineral groups that could form the main structure of a planet if the composition were wildly different. But at the end of the day, these are still those minerals, and the formation of them, they abide by the same laws of thermodynamics and the same style of chemistry, same ionic bonding you would get as you have on Earth.
But I wonder, like, could you, if you happen to be in a part of the Milky Way that was completely iron poor but was rich in these other minerals, could you still have habitability using the capabilities of those other minerals?
Yeah, so because touching into important within astrobiology and the evolution of life, having transitional metals are very important, right? So something that can carry oxygen, bind with oxygen, release electrons, that is an important aspect of metabolism or metabolic pathways and evolution of life. And so having iron is the one in a planet that it's the element in a planet that is in greatest quantity that is able to exchange its valence states like that. But manganese can do that. Many of the other transitional metals, so the metals you find in the kind of center of the periodic table, a lot of these can do that. So if you could imagine a planet that was very copper rich and iron poor, perhaps, or manganese rich and iron poor, perhaps, then that might be your important transitional metal in your metabolic pathways. I'm sure there's some biologists who would scream, no, it's not possible.
But just from a purely geologic standpoint, to say, would you still get? I mean, at the end of the day, what you really want is you want minerals coming from inside the planet, getting up onto the surface, and things like carbon dioxide being pulled out of the atmosphere and pushed into the mantle. And so, if you could have alternative ways of doing that. Sounds like another paper. Sounds like we're giving you 3 or 4 papers for today. So
actually, one of the collaborators on this project, John Wade at University of Oxford, he's thinking about this information a lot, and I think he's got something in a few papers in the pipeline where you're looking at environments where you actually get iron in all 3 valence states, metallic iron, Fe2 plus and 3 plus, all in the same environment, because that's a very rich potential environment for life to evolve. Because you can make exchanges of electrons, you can oxidize and have this energy transfer.
It is interesting how you go into this with these assumptions that the way it works on Earth is got to be the way that it works, and yet time and time again, or the way it works in the solar system, we're finding hot Jupiters, we're finding mini Neptunes, we're finding classes of planets super Earths that we never even knew existed, and it's just changing our understanding of what's possible. And then you're able to then take all of the elements in the periodic table and mush them around and see what they do in weird and different places. Well, we've reached the end of our time. Brendan, absolutely fascinating to talk to you. If people want to follow your work, where should they go?
Yeah, so you can find me on Twitter. My handle is crustal, so crustal and then EVO for evolution. Or reach out to me. I'm at University of British Columbia on the Okanagan campus. Love to hear from people. Going to look into K-stars, so I'd love to hear other suggestions.
Perfect. All right. Awesome. Well, thank you so much for taking the time to meet today, and good luck with your research. Hopefully you'll get some time on James Webb when they start offering it up to geologists.
Excellent. Well, it's been a pleasure. Thanks for having me.
Thanks a lot.